Okay, so we're going to do another example of solving a system of equations using Gauss-Jordan elimination. In this case, we're going to be working with a system of two equations in four variables. Now, for this one, we're going to define an important term. We've talked about this terminology in the previous section, but I'm going to bring it up again here. Notice that the constants in both of these equations are zeros. If you're dealing with a system of equations where all of the constants are equal to 0, we say that this system of equations is homogeneous. Now, homogeneous systems are really, really important in this class, and we use them in a lot of different things. So pay close attention to this. One important property of homogeneous systems is that they never have no solutions. Homogeneous systems of equations will always have at least one solution. They either have one or infinitely many. And the reason for that is fairly easy to see. One solution that I'm guaranteed to have for a homogeneous linear system is what we call the trivial solution. It's the solution where all of my variables are equal to 0. Notice, if I use the ordered 4 tuple, 0, 0, 0, 0, plugging that in, I get 0 equals 0, 0 equals 0. It's a solution, and it will always be a solution for any homogeneous linear system. So homogeneous linear systems, again, can never have no solutions. The question is, do they have one, or do they have infinitely many? So let's work at solving this one. Here's my augmented matrix. I don't have a leading 1, but it's easy enough to turn this into a leading 1 by multiplying my top row by 1/3. And notice I end up with a lot of fractions. You tend to see a lot of fractions with Gaussian elimination, except for those cases where we very specifically pick an example to make sure that doesn't happen. But in practice, more often than not, you're going to be dealing with a lot of fractions. So here's my 1. And what's the next thing that I need? I need a 0 below that. So to get that 0, I can multiply my top row by -5 and then add it to row 2. Here's the result of that. All right, what's next? Well, the next thing is I'm going to need a leading 1 in this row. So here, -8/3, that's my first non-zero term. I need that to become a leading 1, and we accomplish that by multiplying by its reciprocal, which would be -3/8. So multiplying this second row by -3/8 produces this, 1, 1/4, 1, 0. Now, that's the forward phase. The backward phase is going to be one step. So I didn't actually even write this out, forward phase, backward phase. We're just doing this all in one. I need a 0 above this leading 1. So if I multiply by -1/3 and then add to the first row, here's what I get. Okay? Now, I want to point a couple of important things out about this before we come up with a solution. First of all, notice that in each of my steps here, the last column remained zeros the entire time. And that's one nice thing about homogeneous linear systems, is in any of the 3 row operations that we're able to perform on a linear system, we'll never change these zeros into something else. And if you think about it, it's easy to see why. So that last column will always remain zeros. The other thing I wanted to point out is that, and we're going to state this as a theorem in a little bit, this particular system had more unknowns than equations. So what that means is it had more columns than rows. Remember, the columns correspond to the unknowns, the rows correspond to the equations. So what does that mean when it comes to leading 1s? Well, in any column, I can only have at most one leading 1, because Gauss-Jordan elimination ensures that all of my other entries will be zeros. So if I only have 2 rows, like I have here, and again, we can only have one leading 1 in each row as well. If I only have 2 rows, that means I can have at most 2 leading 1s. But that means there's other columns representing other unknowns in this system that are going to have something other than leading 1s. So there has to be free variables in this case. The fact that there's free variables means that I'm going to have an infinitely many solutions. I'm going to have an infinite solution set because we assign parameters to these which can take on any real number value. So let's watch that happen now. We have leading variables A and B, which are the first two columns, and free variables C and D, the third and fourth columns. We take the free variables and we assign parameters to those. So variable C, I'm going to assign the parameter R. Variable D, I'm going to assign the parameter S. Next thing that we do is we take the two rows and rewrite them as equations, but replacing C and D with these parameters. So normally this equation right here would say A plus 1/4 C equals 0. But I'm going to replace the C with an R because that's the parameter that I'm using for C. Then what I can do is solve this for A. A is equal to -1/4 R. Notice A is not just a single real number. Because we have an infinite number of solutions to this system, it's represented parametrically. Similarly, if I take the second row right here, normally I would write this as B plus 1/4 C plus D equals 0. But I replace the C with an R, and I replace the D with an S. So it gives me this, B plus 1/4 R plus S equals 0. Isolating the B gives me B equals -1/4 R minus S. So now all four of my variables are given in terms of R and S. C and D are equal to R and S by themselves. A is equal to a multiple of R, and B is equal to a linear combination of R and S. Now the term linear combination is one that we're going to talk about more in future sections, and it's going to be a really, really important term for this course. But what it means essentially is that it's a sum of multiples of the two variables. It's a sum of multiples of R and S. Okay? Don't worry if that term is confusing now. We're going to talk about it in more depth later. So the next step, or the final step really, is to represent this as an ordered four tuple. So A, B, C, D, I put my solutions for A, B, C, and D into an ordered four tuple, and this is what I get. Okay? And again, remember the way that you use a parametrized solution set is you pick any number that you want, plug it in for R's, take any other number that you want, plug it in for S, and the result is guaranteed to be a solution to the original system. Okay, let's move on. Here's another example. In this case, we're looking at kind of a flip-flopped version of what we just saw. So in the previous case, I had more unknowns than equations. In this case, I have more equations than unknowns. And we actually have a name for both of these types of systems, which will come up later on in the course. If I have more unknowns than equations, like in example 3, we call that an underdetermined system. If I have more equations than unknowns, we call that an overdetermined system. Not going to go into any explanation as to why we call them that or what the purpose of giving those names are. That'll be more relevant later. But let's start by getting our augmented matrix. So 3 columns for my unknowns, x, y, and z, and then a column for my constants. Here's the forward phase. So again, I have a 0 here, and I can't multiply by anything to turn that 0 into a 1, so I have to interchange 2 rows. I interchange rows 1 and 2. And then, we've kind of walked through a lot of these examples already. I'm going to go ahead and let you look through the notes on your own. I post these notes to Canvas so you can kind of study this. But hopefully you're kind of catching on how Gauss-Jordan elimination works, and you can track with me here. I want to point something out about this one. By the time I get to the end of my forward phase, I have 3 rows of zeros in this system. And that's usually going to happen when you're dealing with overdetermined systems like this. See if you can figure out why that might be what's going to happen most of the time. But regardless, remember each of these 3 rows corresponds to the equation 0 equals 0. It's not a contradiction, it just doesn't contribute anything more to solving our system. So once I'm done with my forward phase, the backward phase is really just one step. I multiply my second row by -1 and add it to my first row so that I get a 0 up here above that leading one. And that's this step right here. Okay? So in this case, where are my leading variables? Where are my free variables? Well, the unknowns were x, y, and z, and x and y, which corresponds to columns 1 and column column 2 would be leading variables because they have leading ones in their columns. Z, my third column, doesn't have leading ones in it. So Z is going to be a free variable. And free variables we assign parameters to. So I'm going to set Z equal to T, and then plugging T in for the Z in the top and the first and second equations here, and then solving for X and Y will give me the fully parametrized solution set. So here's what the result would look like, but I'm going to leave the work in coming up with the first and second component of this thing to you. After that last example, you should see how that works. Okay? All right. So I did mention that we would talk about this theorem here. A couple of theorems here, in fact. So the first one is what we call the free variable theorem, and it's specific to homogeneous linear systems. It says that if you have a homogeneous linear system and it has n unknowns, and if the reduced row echelon form of its augmented matrix has r non-zero rows, then the system will have n minus r free variables. Let me go back to the case where we solved a homogeneous linear system. It was this guy. Okay, so in this case, remember we had 2 equations and 4 unknowns. That's going to correspond to 2 rows for those 2 equations. Okay, now coming over here, it says if a homogeneous linear system has n unknowns, well in this example that would be 4. And if the reduced row echelon form of its augmented matrix had r non-zero rows, then the system's going to have n minus r free variables. This augmented matrix, once it's put into its reduced row echelon form down here, there are no rows of zeros. So we have 2 non-zero rows, right? So r, in this case, it would be 2. N, which is the number of unknowns, in this case would be 4. So what this is saying is that because we have 2 non-zero rows and 4 unknowns, then the total number of free variables should be 4 minus 2. We should have 2 free variables, which means we should have 2 parameters in our solution set. That's what we ended up seeing, R and S here. Okay? So, how can we prove that in a more general case? We can kind of start to see why that would be the case by sort of analyzing that example, but let's talk through an actual proof. So by definition, each of the n unknowns in a homogeneous linear system would have to be either leading variables or free variables, but they cannot be both. So what that means is the number of leading variables plus the number of free variables has to add up to the total number of unknowns in the entire system. Okay? Now, if you have r non-zero rows in the reduced row echelon form, then by definition of the reduced row echelon form, each one of those should contain a leading one. So what that means is if you have r non-zero rows in your reduced row echelon form, then that means you have exactly r leading ones. And again, going back to this example, that's what we're seeing. We have 2 non-zero rows corresponding to exactly 2 leading ones, right? Okay, well again, the sum of the leading variables and the free variables has to add up to n, which is the number of unknowns in the entire system, which means if all I want is to know the number of free variables, I would take the total number of unknowns, subtract the total number of leading variables, which we know is r, and minus r, that would represent the number of free variables. Okay, and that's it, that's the proof. One more theorem to talk about here. It says a homogeneous linear system with more unknowns than equations has infinitely many solutions. Okay, so we've actually sort of talked through enough reasoning to understand this. If you remember, we talked about in example 3 that when you have a homogeneous linear system, you can never have no solutions. It's always either one solution exactly, which would be the trivial solution, or infinitely many. So what this is saying is specifically if you have a homogeneous linear system, and if there's more unknowns than equations, remember that would be an underdetermined system, then that would rule out the case of having only one solution, only the trivial solution. It would have to be infinitely many. And let's see why this is the case. So we're going to say, suppose that a system has m equations and n unknowns, and we're going to assume that m is less than n. That's the assumption being made here. Less equations than unknowns, or said differently, more unknowns than equations. Okay? So remember, the number of equations corresponds to the number of rows in your augmented matrix. So in this case, our augmented matrix would have m rows. And that means in reduced row echelon form, it can have at most m non-zero rows. If some of those rows contain zeros, then we'll have less than m rows of non-zero rows. But at most, we can have all m of them being non-zero. Now, by the previous theorem, we can determine how many free variables this system will have. So if all m rows are non-zero, that means we have exactly m leading variables, which would mean we would have n minus m free variables. But the assumption that m is less than n means that n minus m would be positive. It would be greater than 0. Now, if we had less than m non-zero rows in our reduced row echelon form, this would still be true because m would be smaller and n minus m would still be positive. So regardless of the number of non-zero rows we have, we will always have at least one free variable. At least one, because the number of free variables has to be positive. What does that mean? Well, remember, if you have a free variable in your reduced row echelon form, if your system ends up with a free variable, you assign a parameter to that free variable, and then you can plug in any number that you want for that parameter to produce a solution to that system. But there's an infinite number of choices for the numbers you could plug into that parameter, so that would imply infinitely many solutions for that system. That's what's going to complete this proof. Okay, so that should be it for Gaussian elimination. Jordan, and Gaussian elimination, these are tools that we're going to be using for the entire course. It's really, really important to master this here. You should be able to do that through the homework, but pay close attention to the steps, the sequence of using forward phase and backward phase, and you're going to want to get really good at this because this is a crucial tool for the entirety of this course. But that's going to be it for 1.2.